Imagine a ball rolling up a hill. You know that if the ball doesn't have enough energy, it will eventually roll back down. Now imagine a tiny, tiny particle, much smaller than even an atom, approaching a similar barrier. In the quantum world, something amazing happens. This particle can actually pass right through the barrier, even if it doesn't have enough energy to go over it. This is quantum tunneling. Quantum tunneling is a strange and counterintuitive phenomenon that occurs in the realm of quantum mechanics, the physics of the very small. It's like a magic trick, but it's very real and has been experimentally verified countless times. This mind-bending concept arises from the wave-particle duality of matter, where particles like electrons can also behave like waves. To understand how a particle can tunnel through a barrier, we need to think about it as a wave. Imagine the wave approaching a wall. In classical physics, the wave would simply bounce back if it didn't have enough energy to go over. However, in the quantum world, the wave doesn't just disappear. Instead, it has a small probability of continuing on the other side of the barrier, even though it shouldn't be able to. Think of it like this. Imagine throwing a tennis ball at a wall. In our everyday world, the ball would always bounce back. But in the quantum world, there's a chance the ball could magically appear on the other side of the wall. That's quantum tunneling in a nutshell. This tunneling effect occurs because the wave function describing the particle doesn't go to zero at the barrier, but rather decays exponentially inside the barrier region. Quantum tunneling is one of the most striking examples of how quantum mechanics differs from classical physics. In classical physics, the world is deterministic. If you know the initial conditions of a system, like the position and velocity of a ball, you can predict its future behavior with certainty. However, quantum mechanics introduces an element of randomness. In the quantum world, we can only talk about probabilities. For instance, we can calculate the probability of a particle tunneling through a barrier, but we can never say with absolute certainty whether it will happen or not. This probabilistic nature of quantum mechanics is one of the key differences compared to the deterministic nature of classical physics. Section 4. Proof in the particles. Experiments with quantum tunneling. Quantum tunneling isn't just a theoretical concept. It has been observed and verified in numerous experiments. One of the earliest and most famous examples is the alpha decay of radioactive nuclei. In this process, an alpha particle consisting of 2 protons and 2 neutrons is trapped inside the nucleus of an atom by a strong nuclear force. Classically, the alpha particle doesn't have enough energy to escape the nucleus. However, thanks to quantum tunneling, it has a small probability of tunneling through the nuclear barrier and escaping. This is why some materials are radioactive. Their nuclei are unstable and can decay via alpha particle emission. Section 5. Faster than light? The implications of quantum tunneling. One of the most intriguing aspects of quantum tunneling is its potential implications for the speed of light. Some experiments have shown that particles tunneling through barriers seem to do so in 0 time, suggesting that they may be traveling faster than light. However, it's important to note that this doesn't necessarily violate Einstein's theory of relativity. The information carried by these particles still travels at or below the speed of light, even if the particles themselves appear to tunnel instantaneously. While the idea of superluminal, or faster-than-light travel is fascinating, the current consensus is that quantum tunneling doesn't violate the cosmic speed limit set by Einstein's theory. Section 6. A universe of possibilities, quantum tunneling, and the future. Quantum tunneling has profound implications for our understanding of the universe and has led to the development of numerous technologies. For example, it's the mechanism behind scanning tunneling microscopes, or STMs, which allow us to image individual atoms on a surface. It's also crucial for the operation of transistors, the building blocks of modern computers and smartphones. Without quantum tunneling, many of the devices we rely on every day simply wouldn't exist. As we delve deeper into the quantum world, who knows what other amazing applications we'll discover for this mind-boggling phenomenon. The future of technology and our understanding of the cosmos might just depend on our ability to harness the power of quantum tunneling.